have Sven Beyer from Siemens.
Yeah, thank you, Heidi.
It's a second.
Hello? Okay, perfect. Thanks, Heidi. So essentially, I want to pick up where Thomas started in the morning with the great responsibility of the verification side of things with RISC-V. And I want to start with some results first. Let's look at a couple of the usual open source cores where our formal solution called Questa Processor has been applied. So you see quite a few of the cores from open hardware in here with certain bug counts. The Rocket family is also quite prominent here. And towards the right side here, you just have some E number cores and A number cores, which is essentially some of our customer projects. This is mostly the numbers just from evaluation, so that's why it's relatively small. Of course, the customers then apply this on their own going forward, and we don't have the numbers anymore for that, obviously. But the more interesting spin of these numbers is actually looking at what kind of issues are found with Questa Processor. So, of course, you would think about the instruction side of things, right? You have your misbehaving instructions. You have your forwarding in the pipeline that goes wrong. So the typical user-level issues that are, of course, caught with the Questa Processor. But the thing is, we also completely model the privilege specifications. So all the intricate rules about the CSRs and exception entry, exception delegation, masking of stuff.
Okay.
All these small sentences in the privileged ISA that says in this and this mode, this and this field of this CSR is supposed to be tied to 0 or read-only or whatnot. So all this is kind of captured in the privilege part of our model, and it is really a sweet spot because that is typically not so well tested as the instruction side of things. And maybe also to note a little bit, we also have found some issues with the Questa Processor in actually the SAIL formal model, because also this is something we actually try to reuse as much as possible, the SAIL formal model. One more on the actual result side of things. So actually this is from one of our customers, CodaSip. They were deploying a full-fledged processor DV on a 64-bit application core with lots and lots of different solutions. And the one observation that you have typically when applying formal as part of processor DV is this is the one technology that keeps finding bugs steadily when all the others have come to, well, not exactly a standstill, but they become a lot less productive, so to speak. So you would have to put in a lot more effort and resources on the simulation side to actually hit the next issue, whereas in formal you are still able to progress. And yeah, this is also a nice illustration of an intricate issue that was found with this app. It's actually that there was an issue of self-modifying code. So the same PC location got fetched twice, and on the second fetch, some of the decoding information from the first switch fetch was still attached to the instruction. So on the second fetch, the instruction suddenly behaved subtly different than on the first fetch, which of course is a thing that you typically don't really test for. It's super hard to find, but with formal and exhaustiveness, you just find it by default without any additional effort. And finally, on the application side, CVA6, it's also an application core from open hardware. So it's fully Linux capable. And here, essentially, we have just done a proof of concept application of Questa Processor. We'll see that on the next slide, what I mean with this, and found quite a few interesting issues on the privileged ISA side of things about exception entering, debug addresses, and PMPs, and so on and so on. Now, how does it actually look like to apply this Questa Processor? So, of course, we try to make this as easy for you as possible. So we have some capability to extract the architecture, so figure out all the CSRs, and from that also deduce quite a few of the extensions that you have implemented. And then, yeah, there's some guided setup with quite a few witnesses, which essentially enables you within a few days to have a very rough initial setup, right? This is not a setup that enables you to do a sign-off, but it is enough to get your first instructions through and actually start to be productive and find bugs. Because on this small piece that you're looking at, you imply the full formal exhaustive approach. And actually most of the numbers you have seen on the initial slide were actually just from this phase, because here you really start to be productive. So your investment of 3 days gives you quite a few return of investment. Now, on top of that, of course, you will refine things. You will enable all the intricacies of your data memory interface, and over time also enable the asynchronous interrupts and stuff like this. And then, of course, at any time in this road, from initial setup to final setup, you can also enable your custom instructions. We'll see a little bit on the next slide how this looks like, but essentially they are just input into our model like all the standard instructions from the RISC-V specification, and they are just compiled alongside. So if you have simple custom instructions, you can fire them up on the initial setup. If you have more intricate stuff with memory and writing 2 registers and stuff like this, yeah, maybe it's more towards the final sign-off quality setup that you then achieve within a few weeks, or of course on a bigger core, application core, it can actually of course also be a 1 or 2 months that you have to invest here. Now on the custom instruction side of things, I'm just showing here a GUI picture. Typically you would model this on the scripting side of things, obviously, but here on the GUI we see here how a fraction of the xpulp extension is actually modeled. So we have your usual table of decoding, you have a name of the instruction, you have a disassembly syntax, so of course we will also integrate the disassembly then into the debug for you to have a nice experience. And then the execution itself, that's just a sale expression, so to speak, that can be of course arbitrarily complex, can call supplementary functions and so on and so on. And when you specify this, it will just be added to the model and the corresponding assertions will be generated. So to sum up, what you get out of using Questa Processor, if you actually try to start from scratch, you get really a lot of improvement on the setup side of things, and also your first finding of issues within days. You typically don't get that with other setups, so to speak. You get a quite high degree of automation. What we have already mentioned is we have this extraction of the ISA features, so to speak. And then also, of course, whenever you have failing assertions, it's quite hard to understand what's going on. So we have quite some automated analysis built in that will tell you exactly what is going on, what has been updated, what has been expected, and so on and so on. And we'll also annotate the sale model on top of it. So of course, if you model your custom instructions, you could also have made a mistake in the sale model. Then, of course, because it's formal, you get the exhaustive side of things. So, I mean, you are sure to find all the issues, starting with your initial setup, and when you have then removed all the constraints and enable the asynchronous event, you eventually have done the full sign-off quality setup that covers all the instructions, all the exceptions, and the exceptions also including all the asynchronous stuff like the interrupts and the debug events. So essentially, with this, I would then also open for questions. I guess we have time for 1 or 2, or otherwise you can also pass on. I mean, I guess, it's kind of a lunch and learn. I guess you're all hungry or...
Okay, I think they're all happy.
Okay.
All right, thanks, Sven.
You're welcome.